In this exercise, we're going to go over the transient balance equations and specifically just discuss each of these balance equations, and we'll go over an example in MATLAB. Our general equation is going to be what we have in front of us right here. Accumulation is equal to what's coming in minus out plus generation minus consumption. And for most of these problems, we'll have a control volume that we have in particular that we're going to look and examine, so that in and out is all in reference to that control volume. If we want to get fancy, we can always go infinitely deep, and then we approach some of the fluid properties and some of those fluid mechanics, but we're just going to look at things in general. Generally, for example, a reactor would be a good control volume, or a temperature control lab unit would be a good control volume for an energy balance. So let's look at this mass balance first. Generally in mass balances, we don't worry about generation or consumption unless we're doing something fancy and like a nuclear. So we won't have any generation or consumption. And so we'll just have two terms. We'll have on the right our in and our out. Let's discuss species balances really quick now. We're going to track the moles of a species, and so we have all four of those terms accounted for. We've got flow coming in, flow coming out, generation, and consumption due to reactions. Obviously, when we're looking at a reactor, it's hard to measure the total amount of let's say hydrogen within a reactor, just looking at the reactor, but we can measure concentration, and that will affect our rate laws. So we usually work with concentration rather than the actual amount. And the way we do that is we use this equation right here, which basically we multiply by volume over volume on everything. And so we're able to get Na, mole flow rate, times volume, reactor, times volume flow rate, and this right here is the concentration. We'll look at a momentum balance, and that's often used in mechanical and civil engineering. You can think of statics, and basically it's the same principle though. Whatever force is happening is the cumulative force is the sum of all the forces that are happening, both forces that are coming into the system or the forces that the system is exerting, and then obviously generation and consumption. Those are a little bit more abstract, so we can just think of the sum of all forces, and that will be obviously mass times velocity was also equal to the force. In other words, we could think of this as the acceleration is equal to the sum of all the forces, and obviously that includes the direction as well. Energy balances we're going to be working with a lot in this course, especially with our temperature control lab. And so let's discuss this in principle. We have the change in energy in our system right here, and I'll just use my pointer for this. The change in the energy of the system is equal to the change both internal energy, I'll use an arrow, kinetic, and potential energy. And oftentimes when we have something going on, let's imagine our temperature control lab unit. When the temperature control lab unit is running, there's really not a change in kinetic or potential energy while we're heating up that or running it. It's really just a change in that chemical or that internal energy that the U represents. And so we can go ahead and just assume that these two are zero and just focus on that internal energy. If we factor out mass, here we still have the kinetic and the potential terms. And we can look at a little bit more why those two don't change all that much. Well, obviously this is the delta, so right here is the corresponding kinetic and potential terms. You'll notice that we have the velocity is the main term here, and we also have the height, z, and then gravity as well. But you can tell that for most chemical applications, we don't normally have a change in velocity all too much. I mean, flow through pipes for sure, But in most control applications, we're usually keeping velocity somewhat constant, and especially with a temperature control lab, velocity is not changing. We're keeping that thing just on top of the desk, and the height's going to stay the same too. So we're really worried about this enthalpy, this H hat right here. And obviously the Q and shaft work, if we were doing something like a reactor, it'd be something similar. We'd have enthalpy changing. The velocity coming in, coming out are probably somewhere the same, and the potential energy, the height's not going to change too much generally. Obviously, if it did, we could factor those in. But we can generally make the assumption down here, where we just look at just the change in enthalpy right here. So we're going to have our mass and our enthalpy, and we can also make that distinction with heat capacity to factor it out even more. Once we have all these relations factored out into this equation down here, right here, we'll go ahead and zoom in just a little bit. So with enthalpy in terms of mass times heat capacity and the change in temperature, we're able to solve an energy balance in terms of temperature. And that's helpful because we can either predict what the temperature may be, or we can use this energy balance to figure out with the temperature what it is now, what was the input. Things like that are very helpful. And again, this all just comes back to this last equation. Accumulation is equal to in minus out plus generation minus consumption. And so if we go to very basic and then kind of work through mentally, that'll always help us out conceptually understanding the system. So we're going to go ahead now and we're going to look at this mixer right here. I'm going to look at the dynamic response of volume, concentration, and temperature in this well-mixed vessel. We're going to have some constants. Our volume is going to be 1 liter. Concentration initially is going to be 0 moles per liter. And we're going to have an initial temperature of 350 degrees Kelvin. There's no reaction and no significant heat added. But we do have a cooling jacket, so that will help our energy balance. We'll have some heat exchange going on there. So we go ahead and look at it now in MATLAB, and we're going to discuss how we're going to model this problem. Here we have our exercise in MATLAB. We'll go ahead, we have the initial conditions as we discussed before right here plugged in on the initial conditions cell. I always like putting the units in a comment just to make sure that I'm keeping my units straight. And we have a time array that's already provided as well. The first thing to do is to create arrays for our inputs with a step change. And the inlet flow rate was given as an example. So we initialize that by giving it a variable name. And then I usually use 1s or 0s to initialize my variables. And here I'm going to initialize them all to 1s, the length of time, so we have a value for each time point. And that's how many rows. I'm going to have 1 column. And then I'm going to multiply that by 5.2 to make each value 5.2. Then from the 50th point to the end, I'm going to change that to 5.0. You can see I have similar things happening for outlet flow rate, feed concentration, and feed temperature. And we just want to change those within realms that are reasonable and also within the time points. And I generally try to keep things with something like this where it's just just observing effects. I try to keep those times distinct from one another. That way I can tell if at a certain time the effect or the change that's happening is due to a change in feed concentration or a change in feed temperature. It's good to keep those separate. Then we'll create arrays to store the results. Again, I use just 1s. You could also use 0s easily. And then length times, we have 1 cell, or 1 element, I should say, in the array for each value. And I initialize that to the initial value. And that's just so if we reference that, there's no problems. Next, we're going to simulate tank conditions. You have provided the Y0, the initial conditions array, and the syntax for the for loop. Within this for loop, we'll first create a slice of time using time 1 and time 2, and because we don't explicitly rely on time, I'm going to keep that slice the same on each one. It's just telling it the length of time. Then we have our ODE 45 syntax, and that should be starting to become familiar. We have the anonymous function, which has t and y, and then the tank function, which I'll go down and we'll look at the tank function first. In our tank function, we have quite a few parameters. We have time, which is a tilde since it's not explicitly used. We have y, which holds both volume, concentration, and temperature. Those are the integrated terms. That second term is always the integrated terms. And we also have the inputs, which are the outlet flow rate, the feed flow rate, feed concentration, and feed temperature. We also have no reaction going on. We'll look at our balance equations now. Our mass balance is pretty straightforward. We're going to assume that we have constant density. So the change in volume is just going to be the flow rate in minus the flow rate out. And so that relates to the mass balance just because we have the same density. It's actually a volume balance, I guess you could say, because volume is conserved in this case since we have constant density. Next, we have our species balance and our energy balances. Both of these are going to use the chain rule since we have concentration and volume changing per time. Or in the energy balance, we similarly have two variables changing per time. We could write this species balance, for example, as the change in dCA, concentration, times V dt. So because of that, to account for both of those terms, we have this first term, which as we discussed before is the balance on concentration. Feed concentration times volume minus outlet concentration times volume divided by volume gives us our concentration. Each of these terms right here actually gives us the amount of species A coming in or out. We subtract the amount of A that's reacting, and then this is the volume portion, the change in volume and how that relates to the concentration. Since we have this volume term right here, we have to include that portion, or the derivative of that, I should say. Next, we have the energy balance. And again, similarly, we have the energy balance first. And we have, since we're dividing by the volume, we also have to take the derivative with respect to volume. Finally, we'll output the results as a column vector. And we're ready for ODE 45. We'll output our results into t and y, and then y0 will take the final result after the time step. So, at time step 2, for example, if we're simulating from 1 to 2, we'll store the results not at 1, but at the next step 2. So at time 2, we have the volume, concentration, and temperature stored within the y0 array. The nice thing about storing it in the y0 array is that we're ready to go for the next iteration. So for 2 to 3, we'll iterate through, and then we'll store the results at the element number 3. Finally, we're going to plot. We're going to use subplots to do this. The subplot numbering is first the row, then the column, and then whichever figure it is. So we're going to have 3 rows, 1 column, and it's figure number 1. And then we're going to plot each of these plots. So let's go ahead and let's just look at the key and we'll be able to come up with the plot together. Time obviously is going to be time. And then we want to, it looks like our Y label is volume. So time and V. This next one is time and concentration. So time and CA. And then time. And let me see what this one should be. Feed temperature. So time and T. And it looks like we have multiple things coming in. So we have volume and also feed flow rate. So I'm going to do plot. And actually we can just do 2 at the same time. So we're going to go time and QF. That's the fluid flow rate. Here we have concentration and feed concentration, so I'll do Ca and CAF. And temperature and feed temperature, so temperature and feed temperature. Let's go ahead now and let's go ahead and run our code, see how that does, and discuss any results that we have. I forgot that we need both pairs. We need the time argument there. We want to do it in this way. We have x1, y1, and we need x2, y2, rather than just providing it y2, if that makes sense. X coordinate and y coordinate, and I'll know that they're pairs, but we need to give it both parts of the pair. We're in that section again. Great, and we can see some pretty clear step changes and how those affect the system. We can see that volume starts increasing at our initial volume flow rate and then reaches steady state, it looks like. Our concentration reaches steady state pretty quickly, adjusting to what the feed concentration is in a matter of about, let's say, 2 minutes. And similarly with temperature, temperature eventually reaches steady state after a few minutes. So that does it for this lesson. We've discussed balance equations, and then we've looked at using those balance equations to simulate this mixer.